But for our next session, we will be joined by Jonathan Burgess and Dr. Daniel Bain, who will discuss their paper on urban soils in a historically industrial city. Jonathan Burgess is the Programs and Policy Director at the Allegheny County Conservation District in Pittsburgh, where he oversees the district's agricultural tech assistance, watershed farm preservation, and urban soils program. Dr. Daniel Bain is an associate professor of geology and environmental science at the University of Pittsburgh. And again, if you have any questions, we should have some time at the end of the presentation to address them. So just feel free to pop them in the Q&A, which is on the bottom. And we'll try to get to as many as we can. So John and Dan, take it away.
John, you're muted.
And are you all seeing the share screen on here? I'm just trying to make sure.
Yes.
How it's coming through.
Now we're not.
Now we're good.
No, now we're back to presenter mode.
Oh, sweet. How about that?
There you go.
Cool. All right. It's always fun when you can't see what everybody else is seeing. Quite the same. Well, yeah. Good morning, everybody. Thanks for arranging this event, and thanks for putting together such an interesting collection of speakers. I'm always really inspired to listen to young folks, especially people in high school and stuff, and hear about all the work that they're doing. Gives me a lot of hope. But today, Dan and I wanted to cover just a little bit about a paper that recently came out, was published, and part of that research was led by Alex Maxim, who is currently a PhD student at Georgia Tech. She's not able to be with us today for another commitment, but hopefully Dan and I can give a nice overview of the work and talk a little bit about its relevancy to the topic of lead contamination and lead poisoning, particularly for vulnerable populations like children. And add a little extra context to the discussion. So the talk that we're going to be giving today is called Historical Industrial Contributions to Pittsburgh Soil Metals, Including Lead. And we'll give a little bit of background on how we got into this work, talk somewhat about the results, and then get into maybe some implications and next steps for the community and researchers. So probably don't have to tell this audience too much, but why does it matter? Well, of course, lead is a neurotoxin, widely used for a number of products, including household paint, pipes, soldering, gasoline, pretty widespread use in society. And of course, over time, we've begun to phase that out, particularly in 1978 with the banning of lead-based paints. And then in the late 80s, we started to phase out leaded gasoline. So that process obviously has reduced the inputs of lead into our environment, but there's still a lot of legacy contamination here that we're dealing with. But even though there is a large amount of legacy contamination just sort of, in the ground and, in our infrastructure, there's not a lot of research, particularly on the soil side, on lead contamination, soil contamination, and the impacts from historical industrial practices. There is lead testing that occurs around homes through the health department and other organizations. We talked a little bit about, testing water for lead, but there isn't the widespread depth of research that you would expect for this topic, given its importance. And we're not just talking about pipes and paint. In our industrial past, we had, manufacturing of steel products. We had primary and secondary smelters. We had all these industrial sources of inputs, and not just for lead. We're talking about cadmium and cobalt and nickel and other sources of toxic trace metals. So there's obviously an issue of importance and a bit of a research gap in terms of how much we understand it. So primarily, when we talk about lead, as I mentioned, we do think about, contamination from homes, contaminations from roadways where cars were traveling when they were, combusting leaded gasoline. And those tend to be the kind of focus areas that soil contamination research and investigations look at today. Those are the spaces of interest, drip lines, of an old house next to a road or a driveway. But there is a lot of space in our city that doesn't fall within those, two narrow geographies. So while we know a lot about the risks and we can know where to test, around, a home with children, there is a lot of sort of unknown space within our city, particularly, once you get maybe 5-10 feet off the roadways or 5-10 feet away from the house, it turns into a bit more of a blank slate. So, but we do know that there are emissions that are going out there, industrial processes and things. So it's certainly a reason to investigate. So yeah, in terms of background, the Conservation District first purchased an XRF, which is a handheld spectrometer that allows us to look at about 16 different trace metals. So we can look at things like arsenic and lead, copper, chromium, cobalt, sort of a host of things that you might expect to find in natural soil, but you might also expect to find at elevated levels in contaminated soil. So we first purchased this piece of equipment in 2016, and we used it a lot internally at the district for site-specific investigations. So we would go into a community and partner with, say, Operation Better Block, because they wanted to do a project on a vacant lot, or Grow Pittsburgh, or green space groups in communities in the hilltop. And so we're always looking at site-specific areas, a vacant lot where there used to be a house and it was demolished. But we didn't really have anything to compare that to. So we started thinking about the need for a background study in the city. So stepping away from those areas where we know exactly what used to be there based on old, fire insurance maps or aerial photography, or just talking to the neighbors who've lived in the community for a long time, and have a point of comparison, for the areas that might have inputs that aren't just the lead paint from an old house. So in 2019, in an effort to try to get this going with, limited resources and just the fact that it's a big city and we'd have to test a lot of places, we partnered with an environmental engineering and policy capstone course at Carnegie Mellon University. And they were looking for projects that would have some community benefit. We were looking for willing partners in labor out in the field. And so we took an EPA methodology for how to do this background study of soil contamination that had been used in a number of other cities like Memphis and Raleigh and Louisville. And we sort of put it into place here. And the students were very helpful with, with collecting a lot of this data. And so what we did is we divided the city up into grids. So essentially took what would look like a piece of graph paper, laid it over the city, and did that on a computer. And then used a program to sort of randomly select which grids. So we had a random distribution of spaces across the city to pull a soil sample from. And then once we had those locations, we tried to find a site near the center of those squares that we had selected that was undisturbed. So we stayed away from vacant lots, we stayed away from roadways, we looked for parks, green spaces, anything that was unlikely to have been disturbed for quite some time. And the goal is to have a piece of land and soil that's just been sort of soaking up what's been dropping from the atmosphere. So via rainwater, aerial depositions, things like that. So we really just wanted something that was just sitting there for a long timeline, just kind of absorbing what the environment was putting in. And so we collected those soil samples and we dried them, we ground them, we sieved them, did all the prep, and then we tested them. And you can see sort of a picture, and that top photo is an XRF. That's ours, with a little testing stand and little baggies of the processed soil. So basically, this gave us a nice, quick and dirty background analysis, and we could see what the lead levels were in each part of the city, along with the other trace metals that we were testing for. And it was interesting, and Dan will get into the results here, but it wasn't that in depth. So, we realized that we could use some extra help, taking this sort of to a deeper analysis and asking some harder questions of the data. And luckily, Dan and Alex at Pitt were interested in partnering on this type of work. And so at that point, once we sort of coded all our data and our soil samples, we turned the product, the soil, over to Dan and Alex, and I'll let him take it from there.
Thanks, John. And I want to echo John's thanks to all of you for putting together a really nice program. Learned a lot so far already and look forward to learning more. And I also want to say it's been a great pleasure to work with John. And one of the things that we'll get to in terms of next steps is these partnerships between the University of Pittsburgh and organizations like the Allegheny County Conservation District are just, we could do so much more than we could do by ourselves. I mean, having these soils in hand and ready to be looked at made things so much simpler, allowed us to go so much further than we could have if we had to do this all ourselves and find the money to pay someone to do all of this ourselves. And then, things just don't necessarily line up. So when we work together, things go faster. And once John did all of that, we had a relatively simple job. So here you can see a picture of pouring some of these sediments into it's a centrifuge tube. We basically did that. We used that. What we did is we added various kinds of chemicals, various kinds of acids to dissolve these soil sediments and try to understand how much of a whole suite of metals are in there. And then you can see here's the machine. This is an ICP-MS that we use for measuring the metals. We did some of this in-house. We did some of this elsewhere. But there's a picture of me. Make me uncomfortable. John, go ahead. Let's get to the next slide so I don't have to look at me anymore. But so here's a map of where all of these different soil samples were taken. So John explained the process. We wanted to avoid things where we knew there were lead. We wanted to try to figure out how much lead is in places where we don't know that there should be a lot of lead. Is there a lot? Is there a little? Well, so that's the kind of thing that we are interested in. We only did this area within the red box here. You just run out of time. There certainly are questions we have about areas that are out here on the eastern side of that box. We'd like to continue doing this at some point, but there's also some things I want to draw your attention to. So there's these flat areas in the middle of the city. So if you live in Shadyside, if you live in Homewood, if you drive down Washington Boulevard on your way home, you're traveling through these old ancient river valleys. And these areas are a little bit, if you look on both sides of you live in there's hillsides on both sides of you. So these are areas that are low, and that's going to be important later on. And we've outlined it in white. So lots of times when we show further slides, you're going to have the city of Pittsburgh boundary here, and then you're going to have these, we call them paleo channels, but it's these low-lying flat areas. If you're going to build somewhere, you build on the flat because it's easier. So that's where a lot of our people live. So these are two important things to look at as we look at the next thing. So we did all that, and this is what these are the measurements. So this is a map where we've shown what we think are the lead concentrations in the background lead concentrations of soils in a number of ways. So in one, we have the actual measurements, and these are shown proportionally by the size of the circle. So if you see a little dot over here in this map, we don't have anything that's as low as 10. So you'll never see a dot this small on the map. But if you have 1,000 parts per million or 1,000 milligrams per kilogram, whatever you want to call it, it's going to be about like so. And we didn't quite get up to 1,000, but we came close. So 619, things that are well above what the US EPA would call a soil action level for a residential area. So if you have something that's above 400, you definitely should be thinking about ways to mitigate your lead risk from the soil exposures. And as Michelle said earlier, that action level probably will start to crank down as our understanding of soil lead levels and the damage it does sort of cascades back up into our regulatory structure. So the other way that we show this is what's called a Krieged surface. And what that means is we try to look at these things and try to figure out where exactly the different concentrations, so these are the concentration ranges, would come. So you can see on the eastern side of town, we have areas of higher lead concentrations. You can also see in some ways, you start to fill in these boundaries. You can't see my mouse, huh? Sorry. Thank you, John. But the other thing that we did is we did it a number of different ways. Because if you just have lead, someone could say, "Oh, you're just missing out. This is just the cars. Oh, no, this is something else." So what we did a bunch of metals so we could look at different things and make sure that we knew what was going on. So another metal we looked at was zinc. So zinc's not is actually a micronutrient. You wouldn't want to have zinc at these levels because it's also toxic at higher levels. So it's a lot of these metals are tricky because you want to have a little zinc, particularly when you have a cold, but you don't want to have a whole lot of zinc because it's not good for you at high concentrations. There's much less clarity on when you should start to clean things up. This is sort of their best guess in a regulatory structure. The Pennsylvania Department of Environmental Protection suggests that if you have 66,000 parts per million, you should start to clean up zinc. And that's pretty high. You know, the highest zinc concentrations we have are about 1,500 in these background areas. That's not to say that if you go down to Donora or up to Monaca, there's not places where you might start hitting this cleanup level. But again, so these, you see the concentrations of the actual point measurements and our best guess to sort of how these things get connected. Again, you see on that eastern side of town, we're starting to see more higher concentrations in the background. So John, if we go to the next slide, some of that makes perfect sense. So right here on the left, we have a wind diagram. So this is, you take all of the wind records from the airport and you say, which direction was the wind coming from? And it's coming from the west going to the east, and maybe slightly to the south to the north some of these times. Most of these, this is a map of all of the industrial areas that was recorded by the Rivers of Steel National History, the National Historic Site. So a lot of this concentration was on the east side of town, on the west side of town. It was pushed towards the east side of town. Let's go ahead to the next slide. But the other thing is again, we're looking at these low-lying areas. These are the areas that get filled first during inversions. These are the areas that stay filled during atmospheric inversion. So if you smell that stink in the morning, you're living in one of those areas, it's because of current coking facilities and things like that. So the other thing that we think happened is because you kept these industrial atmospheric emissions in these areas, you had more time to deposit it on the soil. So, this is, again, a place where we really need some more data here to really confirm this, but these north-south strings are not necessarily something you're going to see with the normal wind blowing things across hills lifting up things, causing rain. These are different patterns. John, let's go to the next one, please. And so one of the things we can do is we can start to look at the mixes. That's why we do more than one. So what we do is we compare the amount of zinc in the soil and the amount of lead in the soil. And then we also look at sources. So, and the green dotted line is the coal fly ash. So this is something we should have everywhere because all of us were burning coal in the 1940s to heat our homes. The blue dotted line, that's the shale. That's the kind of concentration the mix of concentrations you would get in a normal shale. You're not necessarily going to get 800 and 200 parts per billion in shale for most shales. Most of them are going to be way down in the lower left-hand corner of that plot. Then here's just a coal in general, a bulk coal, and the solid line. But then you look down here, here's a secondary smelter. So these secondary smelters, these are things where you ran out of, you used a battery up, you took it in, you had it melted down, and then make a new battery. And these are not these kinds of big smokestacky kinds of things that you're going to see elsewhere. Right here on the right is a shot of the Hazelwood Elizabeth Street Bridge. And you can, it looked like crap when I blew it up, but right there you can see the Pittsburgh Smelter Company. Right there, that sign there. So it's like you can have these smelters everywhere, but if you start to, John, let's go to the next slide, look at, you start moving this way, you start moving more lead for any given amount of zinc, you're starting to move towards something that looks like a secondary smelter. And so we said, oh, okay, let's map this combination of zinc and lead. And so higher amounts, darker colors, a higher lead to zinc ratio means you're moving more towards the smelter line. So what we did is we plotted that. We made these surfaces in the entire study area. Then we plotted some groups in US EPA back in the early or mid 90s, came up with early 2000s, came up with areas they thought there might have been historical lead smelters. And all of a sudden, you know, this lead smelting in these valleys, you know, these are places where we should probably be more vigilant. You know, the one down in Hazelwood looks a little odd, but we think that might be because of the coking that goes on there. We get more into that in the paper. We unfortunately don't have time to do that today. So with that, I think I push it back to John and talk about implications.
Yeah, so you know, essentially, you know, one of the things that you know Dan was summarizing is just, you know, how these patterns emerge, how they connect to surface, you know, topography and geography, and then, you know, the connections to these industrial facilities. And that's really something that we were very interested to get into, because so much of what we look at is just, you know, does this residence or this community have lead service lines, which has obviously been a big focus in the last few years, or, you know, does this house have exposed you know, lead paint that would be a high risk to a child? But it's sort of what else is out there. You know, how can we think about risk as well as mitigation efforts in sort of a multi-layered way? And so that's kind of what we were trying to get at with this is, you know, we have site-specific data. Now we're starting to chip away at the background data. And so we know that you know, in addition to areas where we have older homes, where we have homes that maybe experience, you know, lower, you know, grades in terms of their structural integrity, or the, you know, paint flaking on the outside, areas with higher blight, you know, there are a number of risk factors, you know, that, you know, the health department considers when they, you know, decide what communities might have higher risks for children, and what types of, you know, factors go into, you know, elevated blood lead level risk. And so we're just trying to sort of add to that conversation. And so in summary, you know, these kinds of paleo channels, these low-lying areas, concentrations in the East End, areas that are connected to wind patterns from secondary smelters, are just another thing that we need to be looking at. Because, you know, while some of the levels that Dan was walking through were on the lower end, and a number were certainly above action levels, but in that kind of middle end, you know, those are largely driven by these types of processes that we had here today. So if you can think about these risks plus those site-specific inputs from paint and gasoline, you know, you start to get, you know, ever increasing volumes of exposure, you know, in, say, a child's day-to-day activities. You know, what are they tracking into the home? What is in the home? You know, what are the sort of the vectors of exposure that impact them throughout the day? And what does that mean for how we address, you know, lead in our communities? So certainly a big takeaway is secondary smelters. Areas that are around secondary smelters, you know, come with higher risk profiles, and that should be a part of the conversation when talking to those communities and, you know, when trying to mitigate risk in those communities. So in terms of next steps, you know, a big thing, I think, for this research is to broaden the sampling, particularly in the East End, in the hilltop communities as well. But I think there's certainly a lot of connectivity to these secondary smelter facilities, and some of the testing was a little light on kind of the edge of the city there in the East End, just because of the way that the random selection played out. So I'd like to fill in some of those gaps. We need more research on bioavailability, you know, how easily lead in soil can move into, you know, the bodies of people. Typically soil acidity and other factors have a role to play there. You know, not all lead that's ingested as dust enters the bloodstream. So we need to understand more about that pathway from soils to our bodies. You know, educating around these secondary smelter areas, coming up with, you know, more nuanced soil best practices for people that are either redeveloping spaces, working with the dirt, and also just have kids. And ideally we'd like to, combine this data with that site-specific data that we talked about earlier to create a more well-rounded risk profile. But yeah, as Dan said, one of the big things that we've learned throughout this process is that, especially when we all have limited time and resources, these types of, institutional and community partnerships really have a role to play. It's citizen science and hard science kind of merging together in a way that provides real benefits to everybody and sort of maximizes, expertise and community resources. So that's something we'd really like to do to sort of keep tackling the problem of contamination. So with that, I think we'll take any questions.
Awesome. Thank you so much. I had a couple questions myself, as we have just a couple minutes. First, I just wanted to know, in an ideal world, how would you like to see policymakers respond to these findings? What do you think this means in terms of creating new policy?
Well, I think, a lot of, when you talk about funding and policies for lead, a lot of times, it's, there's some outreach and education focus with the health department. There's addressing specific after the fact lead poisoning in children. How do we address health problems that we know about when they actually appear? I think, a little bit of preventative care goes a long way. And so in this case, I think not waiting until kids are poisoned, but using research to identify areas that have elevated risk and then putting money into just removing the lead. So I think, with soil, that means you can't just ignore vacant lots until a developer wants to come in. These aren't fenced off spaces. These are areas and communities that people engage with on a daily basis. Kids play football on them, people track across them, people garden in them, people use them as extensions of their yard. So I think sometimes, it's very easy to think about blight as just a replacement process, but until that replacement appears, people don't always, have a solution or have an interest in doing something with the space. So I think for us, it rises to the level of something that needs, action sooner than, redevelopment would drive. So, more resources for communities, more resources for institutions to, mitigate, cap, replace contaminated soil and identifying it in communities that have elevated risk.
And I guess I would add that there has to be a way for, a lot of these mitigation techniques really depend on individual property owners being able to control the contact with these soils. So, we have to get a better way to sort of negotiate that process between a landlord and a renter, because the renter does not have that control, and the renter just, so there's got to, that system is not, I don't think, working as effectively as it could. So, I think that's a policy gap that needs to be addressed, particularly in areas near some of these historical contamination, historically contaminating facilities.
Awesome. And then I'll just ask one more quick question. Did you guys consider any environmental justice aspects to this research while you were looking at it, and how it could affect different neighborhoods and just how environmental justice plays out with this research?
Definitely. But it's, the conversation, this is really one of the first things that people, so lots of the conversation ends up being, okay, we know where lead is, it's near the old houses, it's near the road, so we don't need to do any more thinking about where the lead is. So, basically we make all our decisions based on what's happening at those two spots. In the in-between, we have a poor idea of what's going on. So, our first, this is sort of the first step. The first thing we're saying is, look, there are these sizable concentrations areas that are not close to where we've been looking. So we probably need to look more broadly. And, one of the things that always at the forefront of the mind is that Homewood area was blockbusted more or less during when they moved people out of the Hill District. That's right smack dab in the middle of one of these historical river channels. It's an area that gets inverted. Unfortunately, we don't have the data right there to really make it a loctite case. So I'd really like to spin up and really like to comment on that, but I don't know that I think this is what's going on, but if I started doing that, people would be like, well, Bain started talking before he knew it was exactly going on. So I think definitely there are spots where this will intersect with other, things like wet basements and all these other stressors that are going on. And I think there is definitely that dimension there. Just with this the way that this, the flip side of working across these things is sometimes these data decisions are made for one reason, then you end up using the samples for another reason, and then you can't give the perfect answers you'd like to give. But definitely it's on our radar and it's something we want to keep thinking about.
Awesome. Well, thank you both so much for joining us today. The paper is out if anybody wants to go and read it themselves. I can pop the link in the chat to the paper, but thank you both so much. It was great to have you join us.